And as usual, I do have a lot going on the bench behind me. It's kind of a mess. I have dabbled a bit with EPROMS before, but I did get into an issue when I filmed my last video about the 5170 IBM AT, and it's about the EPROMS. I did mention this last time. It's about the 250 versus the 190 nanosecond delay. I used 250 chips. The IBM reference manual said that these chips needed to be 190 nanoseconds delay. And what actually is this delay? Why did this work with a 250 nanosecond chip? And what's the difference between worst case and what we actually can measure? And how is this measured? So I dug into this a bit. I do remember some of these things from back in the day, but I wanted to make sure that I have understood this right. So I did dig into this, and I will go through a datasheet for an UV-EPROM, and I also will show you some experiments that I did on the bench. This is not a full experiment, this is not a full verification of a datasheet of an EPROM. I just wanted to confirm that these devices actually are faster than their, what should I say, maximum parameters that's said in the datasheet. So I dug up 3 different 2764s and put them to the test. First I will show you approximately what I did couple up on the breadboard. It's quite a mess here, and I will show you what I actually did with this and give a short explanation of what I'm going to do here. So let's dig into that. Yes, I'm going to draw up a basic circuit here, and I'm going to use TTL logic, and I'm going to use a 74 HCT14. It's a Smith trigger inverter as a simple oscillator. I don't need this to be perfect, but it's quite easy to tune this kind of device, and it only requires a capacitor down to ground and a resistor from the output to the input, and it will make a signal, and I can buffer the output through another gate. And I'm going to draw up 3 counters. These are BCD counters, binary counters, not BCD counters, sorry. And they are going to count up and be cascaded. So I'm going to take the ripple out from, or carry out from the first, and add this to the clock of the second and the third, so on. So that I will have 12-bit counting. And for this to actually count up a 2764 chip, you need a 13th address line, but this address line I'm just going to either switch to low or high. It doesn't matter much, because the pattern I'm going to put into this EPROM will be continuous and it will be in smaller chunks. I do think I will count from 0 to 255 and run down to 0 again and just do this on repeat. Then I will get synchronous pulse on each of the data outputs, and it will be a high frequency on data bit 0 and a slower frequency on data bit 1. And I'm going to draw this with just one 2464, the other will be coupled in parallel. So that's the basic circuit, and I might need to modify this. I probably need to put in another counter to divide the frequency when I'm going to test the chip enable output. Then I need a separate clock on the, or not a separate clock, I need a clock with a faster clock on the chip enabled than I need on the address bus. I need at least to have it delayed so that I will have a stable address when I put the output enable low, as we will see when I go through the data sheet for this. But this is just the basic idea. I'm probably going to modify this a bit on the bench. I'm not going to go into detail because this is not a construction video. It's about documenting the delay and explaining my process, how I'm going to go forward, testing this delay according to the data sheet. So this is our basic circuit. I do think it will work in some fashion. And these signals that I need to put on these counters is the 2793 counters. They can be preloaded and stuff. I'm not going to use those. I'm just going to use the count up function, the carry out function, and the other enable lines just to make it count. This is the choice I have to tie the 813 line high or low. And I'm also making a switch here to switch in, so I either put the output enable constant high or I use it from a clock. With the constant low output enable, I'm just going to check the delay between I put an address in and I get stable data out. The outputs, I'm not going to connect them to anything. I'm just using them to use the logic probe and the scope probe just to measure out the pulses. I could of course tie them to something to make them less prone to noise and stuff, either through down or to 0 or to high with the 10k resistor or something, but I'm just going to keep them floating. Yeah, I mess up a bit here when I'm drawing the outputs from the data bus. I'm actually going to program this EPROM with a counting sequence from 0 to FF, and then it's going to loop back to 0 again. And that makes the pulses divide the frequency by 2 for each step, and I'm messing up here, so I'm doing this several times just to give you an idea what's going to output. The last one that I draw in red is something that will be approximately what we get. The frequency is calculated by a formula that is stated as 1.2 divided on the resistor times the capacitor, and you get the answer out in hertz if you enter the resistor in ohm and the capacitor in microfarad. But it's not entirely true because the HCT device has a little bit other characteristics. My experience is that the frequency will be a little higher, so it needs some experimentation. There probably is another formula for the HCT and not the normal LS version of the 7414 chip. As the delay is 250 nanoseconds, that means if I just have an asymmetric signal and I do have a 250 nanosecond delay, the absolutely fastest frequency I will be able to run this through is the 1 divided by 250 nanoseconds, and or in seconds then, and I will get the frequency, and this frequency will be 4 megahertz. And of course, if you have a 50 duty cycle, you have a 250 on time, and you have a 250 symmetrical pulse, it will be 1 over 500 nanoseconds, and that will be a 2 megahertz frequency. But I'm going to test this with a frequency of about 1 megahertz, I think. Yeah, I will not show you the actually coupling on the breadboard, but the first circuit I drew up here is exactly the same as this drawing. Of course, I do have 2 EPROMs here that are coupled in parallel. It makes it easier to do the measurements. But before we start measuring, let's go through the data sheet real quick. Yes, there really is no limit to the boring task I'm going to cover on this channel. And this time it's a bit more about EPROMs. Because I did a video about the IBM 5170 AT, and there was some unanswered questions about the delay time and the latency on EPROMs. And there is a number that is given here for every EPROM. This is a 180 nanosecond device. The slowest device you could use on an 8 megahertz AT was 190 nanoseconds. The chips I actually used was 250 and they was just working fine. So I thought I had to dig a bit deeper into this. And I know a bit of this from before, but there still are some unanswered things here. And the reason why I took the 2764A is that is a kind of EPROM where I had some different vintages of this chip laying around. So I found devices that was from 120 nanoseconds to actually 300, and I even think I had something that was 350, but I was not able to get that to work. And there also is some other problems with these older EPROMs. This has a programming voltage of 12 volt. A lot of the older devices has 21 volt as their voltage, and that is not something that the TL8662 programmer can handle without some modifications, at least theoretically. And there even are some older devices. I do have some 2716 and 2732s that actually requires 28 volt programming. So let's dig into today's topics. And the 2764 is a EPROM I used a lot back in the Commodore 64 days. It fits exactly in the normal EPROM window for standard EPROMs, and it's 64 kilobits, and it's arranged as an 8-bit device, so it's 8 kilobit times 8. And we do have some abbreviations here that is useful to discuss, and it's the naming of these pins here. This P is most often called PGM. This E is often called chip enable, and this G is most often called output enable. We will see more of this down below. And this is the datasheet from an ST device. I think this was a rather good one. I have a similarly good one from Intel, but it was a bit, it was a bit grainy, the PDF scan I had of this device. So this ST device had a nice datasheet, and this I downloaded from FutureLex webpage, I think, and they presented this as the generic 2764, and they are about the same, but I did discover some differences, but they are mostly the same. Here they tell you the difference, that the chip enable is the E line and the output enable is the G, and that they are used to control the output of the chip. But there are some differences between these, and that the chip enable should be used for device selection, as not having this enabled at presenting this high will drop the power usage from 75 milliamps to 35 milliamps. And it also will put the device into a 3-state output mode, so that the data lines won't affect or draw current and make havoc on the data bus, and you don't need any additional buffers on the output. So use the chip enable to enable the chip via address decoding, and connect the output enable to the read-write signal on the control logic. And this also can affect the delays. And I did put a small circuit on the breadboard to test this, and they do have some notice here regarding the electrical condition of these chips, and they recommend that you have as close as possible to the device. 4.7 bulk electrolyte capacitor should be used between VCC and VSS for every 8 devices, and they also point that you should have a 1 microfarad ceramic capacitor for every device, and I did not do that on my breadboard. I used the 100 nanofarads or 0.1 microfarad devices that I normally use as decoupling devices. But this might explain some of the noise I had in the transition phase on at least the 300 nanosecond device. That also was the oldest and probably the most power hungry of the devices I had. And this chip has, of course, a lot of operating modes. You have the read mode that we are going to concern us with in this video. You have the output disable, and that if you put the chip enable in the high state. So the chip enable in the high state will decouple the data bus, and they call this high set or high impedance output on the data lines. And you have the program that is actually putting things into the chip, and that requires that you have a voltage on VPP. VPP on this EPROM is 12 volt. And you also do a VEL, that is a programming voltage, into the P signal, the PGM. And you have this in a low state, this in a low state. And you have the verify, and this I wasn't actually aware of, but you actually do the verify with the VPP at 12 volt stage. I thought that the read mode and the verify mode was the same, but apparently is not. Of course it has all the same conditions as this one, but it keeps the VPP at 12 volt. And you have program inhibit, and that's a high impedance mode, so you don't get anything on the data bus. And you have standby, that also gives high impedance on the data bus. And you do have this electronic signature, and that is the one that is called device ID in the application for the TL866 programmer. You often, if you have China devices, or if you can't find them in your list and you have to do some experimentation, you do click off that you don't want this ID to be read. And this is a special mode where you put 12 volt on the A9 line, and then you can read out on the data bit the manufacturer code on this. And if you see, the A0 line should be used in addition, and this is normal TTL levels. If this is low, you get the manufacturer's code, and if this A0 is 1, you will get the device code. And the device code is what tells you what model this is, and this tells you what vendor it is. And this is the one that is used on the TLL866 program. It's the manufacturer's code. So some useful information there, especially if you are going to program the device. Back in school, I actually did try to program EPROMs manually. It was old 2732 devices, and we put them on a breadboard and we programmed in some words on them and read them back just by applying the signals manually. And it was kind of an interesting lab experiment. And they also specify some of the measurement parameters, and this is important when you are going to measure delays and stuff, because this is the parameters they actually measure against, and they count a high as 2.4 volt. So the delay time is not from 0 to 5 volt. If you have a curve that goes like this, and you have 5 volt here, 2.5 here, and 0 down here. So it actually, this timestamp you are looking at to see the delay, not the full 5 volt. So it is when this reaches a stable high state, and that is 2.4 volt on the output, that is when you count this as an output delay. So the delay is measured between this level, not that level, as I would think would be the most appropriate thing to do, but of course electrically this makes sense. And they also say that you have some capacitance equivalents on these buses, and that is of course important if you design a high frequency bus and you are going to load it with several chips. You need to know what kind of delays and parasitic noise you will get because of this capacitance equivalent of the outputs and the inputs. And this is the important waveforms. I will couple them together with this table down here. I will show you that in a second. We will go through the pulses and I will explain. But first, you do have some currents here. And this is what I meant with the chip enable state. If the chip enable is in high impedance mode, you have 35 milliamps, and if it's enabled, you have 75 milliamps. And these huge differences in current draw will need a large reservoir capacitor in the near vicinity, otherwise you will drop the current and we will get a negative spike like so on the VCC line when this is changing from 35 to 75 milliamps of power drain. Yeah, and here they also specify the output high voltage as minimum to 2.4 volts and the output low voltage as maximum to 0.45. This we are going to dive more into, and this is actually a continuation of this table. You have the 25, that is the 250 nanosecond device. You have the 300 nanosecond device and the 400 nanosecond device. I didn't even know that existed. It's actually 450. Yeah, you have some programming modes and programming AC characteristics. We are not going to dig into them. And the same with the timing diagram for the AC waveforms. And you do have a fast programming flowchart. And this is why you select the exact device in the TL86 programmer program, because it will use these fast programming algorithms on the modern chips. Otherwise, I can just fake them by changing the delay times and the pulse width and so on. So here you say that it's a 1 millisecond pulse, and that is in the programmer. You specify that as a 1000 microsecond pulse to program this. And this 3 millisecond programming pulse, you don't actually can set that in the MiniPro programmer. So this has to be faked, or you have to program it several times, as we discovered. Yeah, and the verify, here I was reading that you have the 12.5 volt when you actually do the verify. And it stated how you do the electronic signature and stuff. We already went through that. And this is some of the specification and the marks. You can check your device. And the .1 is the 180 nanosecond device. The .2 is the 200 nanosecond. If it's blank, it stated nothing. So this is the default device, is 250 nanoseconds. And .3, 300 nanoseconds. Temperature range, we don't concern us with that here. And this is just some symbols for the measurements of the standard DIL package. We don't concern us with that. But this is what I wanted to show you about the timings. And this is just a page I inserted into this PDF where I show both the table and address and data line outputs on the same page here. And this you have here, the TAVQV. That is this one. And that is the delay from when you put the data and the ship enable before you get a stable data out on the data bus. And that is here said to be 250 nanoseconds. And then you have another, and this is the same timing. For you can both say that this is for the address line and this is for the ship enable. And this is a bit different from some vendors. Some specify only this time for the delay. But this tells us that this delay and this delay is the same. And this delay is 250 nanoseconds. From when you put the ship enable low, you will get 250 nanoseconds. But if you keep the chip enabled at all times, it still counts as a delay from when you have stable data on the address bus before you can get the data stable out on the data bus. And you have another delay, and that is if you use the output enable, that's the GLQV, and GLQV is stated to 100 nanoseconds. So on this 250 nanosecond device, the actual delay time, if you don't use the ship enable, is 100 nanoseconds. So if you have a stable address in this area here, you have put a stable address on the address bus, you will have 100 nanosecond delay worst time from you put the output enable until you get stable data on the data bus. And the three other measurements that is here, is from you try to turn off things before you can count the data out to be invalid and to be in a high impedance state. So if you use the chip enable, that should be high impedance state, and that is the delay that you have here. From this goes high, you have this delay before you can make sure that this does not make noise on the data bus for other devices. So if you have more than one device that is affecting your data bus, you need this to be decoupled for this long time before you can use the data bus for some other chips. That is the measurements here. So basically what we are going to measure here is two things. I'm trying to measure this and I'm trying to measure this. And I'm going to do this by using the chip enable coupled to a counter, and I'm going to couple all the address lines to a counter that counts from 0 in 12 or 13 bits, and I'm going to program an EPROM that gives me a cyclic signal on the data out so that I can inspect this. So then I'm going to show you real quick what I did to the EPROM, and then I'm going to just start measuring on things, and I will have to make some modifications on the board as I go along. But basically this video is about the measurements, not the circuit. To prepare for this video I needed to make a file and a setup for this, and what I have done here is that into this EPROM I enter this manually. In fact, it didn't take much time, but here there is a counting sequence from 00 to FF or 255 in decimal. And what this routine will do is that will loop through to FF, and then it will start on 0 again. And I have filled this in on 64 kilobit or 8 kilobyte EPROM, where this is repeated 8 times to get it filled to the end. So I only needed a very small EPROM to make this, but I don't have many EPROMs with a size that is less than 128 and 64, also 27 64s, that actually are doable with this XKey Pro TL866 EPROM programmer, because it only enters 18 volt. Well, some of the older devices, some of them even demands 28 volt, but a lot of them demands 21 volt. And what I did here was that I actually programmed an EPROM that was meant for 21 volt, sorry, with this burner, and I put it on 18 volt, and I put the maximum delay here, and I put this to 5.5 volt. It should have been 6, and this also. I do think this is specified from 5.5 to 6 volt, and then I put this on the maximum, that is 18 volt. That actually was enough to get things started, but I had to overwrite this EPROM 6 times before I got the desired result for the EPROM that was meant for 21 volt, sorry again. And this is a slower device. It's meant for, it is marked with 30, that is probably translating to 300 nanoseconds maximum delay on this. So I wanted a slower device, then I had to take an older unit. And the older unit means the higher burning voltage. So the programming voltage, 21 volt, but I managed to get this through with 18 volts and several repeats. I think I did this 6 times to make this. And the first time it stopped, I think, on byte number 2, and then it started on byte something 1E, I think it was, and then it went further and further each time. I did a verify afterwards, and it seems to operate perfectly. If it's a less storageable or long-lasting result with burning with a lower voltage, I'm not really sure. I don't remember how the chemistry was for these devices, but I do think when they are flipped until they receive some charge in the form of UV light. And the other prom that I'm testing here is a newer device. I do think it has 120 or 150 nanoseconds access time, and this was burnable with 12 volt. So I have two EPROMs prepared with the same pattern inside here. So I could have used all the small EPROMs I have. I do have 2716s, 2732s, and of course the 64s, but I was not able to, or I didn't try. I do have some 2732s that has also the 21 voltage marking, but I never tried that. I wanted two equal parts. So that's what I did with this EPROM. And I did this file by just cut and paste. I marked this with the copy, and I just went to this byte here and marked this as paste. And then I did two of them next time and so on. Interesting to see here is that when I come to 20 here, 20 is space in ASCII, or 20 hex. So here you can see the ASCII characters is looped through here when I do this, and 41 should be an A, or 65 decimal. So just a short introduction what I did with the EPROMs here. And the EPROMs, the counting here is meant that I should have a bit shift that changes every one count on the least significant bit, and every other on the data 1, and every 4 time data 3, every 8 time, every 16 time, every 32 time, and so on until we reach D7. So I could have used only the first 256 bytes and used only 8 of the address bits and just tied the rest to ground and used this, but this was easier, more flexible. And I do also consider this best practice, because if one of the other legs is floating or have a bad contact, I will still get the right result. And with the other legs, I of course mean from A8 to A12, as only the A0 to A7 is used to count to FF. Yeah, sorry about keeping you in the dark, but if you will be able to look at the screen on the scope, you do have to bear with me on this. The setup here is that both the output enable and the ship enable is tied low, so that if I keep this here, it should be the same on both. And this is the lowest address bit, A0, and this is the 0 data bit. So here you see the delay when I put out an address, how long time does it take to put out the output. And this is the 300 nanosecond chip. You can see here it takes about 50 nanoseconds. About that, one square on this measurement screen here. And on the faster device, you can see it actually takes longer time. And this is a 120 nanosecond device, and it takes longer time. This is about 150 nanoseconds. No, it's not. Sorry for that. It's about 70 to 80 nanoseconds. Just this delay. And something strange is if that I tie this output enable pin to a frequency, I will still be able to measure the same, but you can see the delay actually goes down. So I'm not sure what we are seeing here, but the delay from when I put a valid address until I get a valid data, when I do pulse the output enable synchronous with it, it actually drags down the time, and that's quite strange. And the same on this, they follow each other, so this is a longer time period, it's about 80 nanoseconds still on this, but this device here, it's much faster. So not every vendor of PROM is working the same, and I'm also going to try with this. This is a 200 millisecond device with the different vendor. This is an ST device, and I do have some trouble with my breadboard, I can admit that at once. If I use my scope probe here to probe the lines, I do from time to time, this is one of the address lines, I do have some trouble with that. And that is why I only measure on the lowest data bit and the lowest address bit, because it doesn't matter, because these two changes every time regardless of the other counters. But I will have some trouble with a binary sequence on the other outputs. So I do have to, this breadboard, it's very, very old. It's at least 35 years now. It's actually bought in 1987 is this bought. And so it's actually almost 40 years old. And I do have some trouble here. On this ship here, for instance, I couldn't get one of the address pins to stick, so I just botched this through with solder. But I will check now to see if I can make good enough contact here that I will be able to measure something on this. First check the power and the other control pins. They should be okay, and this should be pulsing and this should be low. So this should give an output. And let's see here what we got. Yeah, you do have some noise here on the line. I can try to tie this better to ground. Of course, high frequency on a breadboard is always bad, and if you have a breadboard with some marginal contacts, it's even worse. Yeah, I didn't get rid of any noise here. I don't know if this is parasitic signal or not, but here you can see this delay is about 80 nanoseconds, the same as I had with, no, this is actually slower, and this should be slower than this one. And if I take away the pulsing and tie this to permanent low, the output enable, I will get about the same on this and the same on this. So this mystery device, that should be 300 nanoseconds. If I don't use the output pins, I just tie this permanently and use it to drive the data bus. It actually gave us a very small delay. And just to explain some things, to make these result, I actually had to put in another counter. It's put like so. It's a 7493 that I actually used to divide the output enable or ship select pin when I measure with that, so that I get another frequency on the counting on the output device, so I can keep a slower clock on the counting out on the address bus than I do on this enable signal to be able to measure something. So I did do some things there to make this viewable result. But strange things, you do have some parasites, and I saw that when I increased the frequency. If I tried to do this on about 2 MHz on this breadboard, things were getting nasty. And I even tried with some contact cleaner on the breadboard, but the contacts on this breadboard, and this is the scissor kinds of contacts, they go like this. The clamps that this is inside here, and you have the opening on the breadboard here, like so, and the legs is sticking through here. And if this don't get a good enough contact, and you probably have some contacts down here that it should pass and make contact, but it doesn't work. Sometimes on the cheap breadboards, if I put a too thick pin down here, this will happen immediately. But this one has been working rather faithfully for a lot of years. But the last time I used this, I also had some problems. And I do have another one that is the same vintage as this one. And this was bought back from a vendor back in the day. It's the same kind that we had in school actually. So I didn't know about every other vendor. I thought this was a very neat idea when I went to school, and I asked the teacher where they had bought them, and I bought mine from the same place. And I actually bought 2 of these. So I do have another one. And I also have one other that is quite old, but it's in very bad shape. So the next time I will doing some breadboard work, I will use another breadboard, at least if there are large ships involved. Because when you are doing quick measurements like this, you don't want to do this kind of fault finding on your breadboard. You do want your breadboard to be the stable part. And even on this one, I probably have some pins. Yeah, there I have one pin. It's not figuring out what it should do, and the signal that going into this is this one. So it's working. So both of these have pins that is not counting as they should. Yeah, here I have another one. But as you saw, I made this repeatable image, so it doesn't matter much if the most significant bit is counting. But as I did measurements now on the least significant bit on the data bus and the least significant bit on the address bus, it's changing every time anyway. So that's it. We have done some measurements. To summary this up, we did have a large delay when I was measuring this with a pulse, and this device that is marked as slower, a 300 nanosecond device, in most cases actually was faster than these devices, especially if I did an early strobe on the output enable and kept it low, and then I could take the changes on the data bus immediately. It was only a couple of nanoseconds. So you can trust these markings. They probably do keep within some spec, and you also have the parasitic noise that you are getting. You can almost hear it here on this one, but you will see it very clearly when you have here. This is clearly a low signal, and if I try to focus or trig the scope, only I can just keep it like so, and just put this like so. You can see that it's blinking in with some parasitic noise. So there is some timing issue stuff going on. And of course, if this happens on a data bus, if the system is sampling this fast enough, it will get unstable, to put it at least. And this is the fastest devices. This is 200, 120. So could be the breadboard. I'm not sure, but I did be able to measure what I came for, and that is not every EPROM is the same, and most of them perform better than expected. But I will revisit this sometime, and probably it's better if I do a short setup with an Arduino or something where I can program the outputs better than I can without applying a lot of logic here. So that's it from the bench. Yes, and that was what I was going to cover this time about EPROMs. I'm not totally satisfied with the results. I did expect some better, that this was more according to the datasheet. Of course, these components are old. They could degrade, but that every one of these should behave a little different. That's strange. But then again, I have looked into some of the data sheets, and I mentioned it earlier that there are some differences among the data sheets. And as we noticed, yes, there are some differences among the EPROMs too. And of course, not every vendor make the exact same device, but the 27 series of EPROMs is about as close to a business standard as you can get. But I have looked into some of these data sheets, and there actually are some differences, and especially what surprised me was there was some differences with how you measure delays, and also there are some differences with the control signals. Some of the devices is actually using the program pin also as a sort of enable pin in read mode, and that surprised me. And also that there was a difference between verify and read. It's not the same. Not every vendor has that in their data sheets. And will I be revisiting this again? I'm not sure, but I do have some thoughts about mapping this a bit better. As you might know, I have made some videos before about EPROMs, and I use EPROMs to a lot of different stuff. If I'm missing a decoder and encoder of some kind, an EPROM is a very easy programmable device, and it can be used to all kinds of integrated logic if you are just programming it yourself, because there is no description language to put logic into an EPROM, but of course it's possible. But it's kind of more of a brute force lookup table way of doing things. But this video has gotten far longer than I intended, but I hope you have enjoyed the content. There has been a lot of useful information here. And even though this information might be old and outdated because EPROMs are not longer made, they have been replaced with at least 2 or 3 generations of EEPROMs afterwards, and they are performing better, they are easier to use because you don't have to use the UV light to erase them. And this is another interesting side note. In fluorescent light, you will be able to erase an EPROM in about 3 months' time. But you will be able to make bit fault on a device in fluorescent light in less than a week. So always cover the window, and in bright sunlight, in direct sunlight they actually said, it's even shorter. You can make a bit fault in less than a day. And of course this also differs from generation to generation of EPROMs. The old ones had bigger windows and they also had bigger dies, and I do think they needed more UV light to actually turn the cells. And all the cells in an unused EPROM is FF, and you program them as a 0. So you're programming all the zeros and you leave the ones behind. So that's it for this video. Hope you like the content. Please like and subscribe. Please look at some of my older videos, browse through my channel and see if there is something you like. Please leave a comment. Until next time, take care.